All right, so in the previous video, we took a look at an example of finding the volume of a solid whose cross sections were equilateral triangles. But the majority of the examples we do in this section will have circular cross sections. And the reason for that is because they arise in kind of a natural way. We're going to talk about these things called solids of revolution. So a solid of revolution is what we get if we take a region in the xy plane. So for example, this particular region is bounded above by the function y equals square root of x and below by the x-axis. And it's the part of that region that lies between 0 and 1 on the x-axis. So we get this sort of blue region here. We get a solid of revolution if we take a region like this one, bounded, or sorry, in the plane, and we revolve it or we rotate it about one of the coordinate axes, or more generally just any line. So in this case, if I were to take this region and rotate it around the x-axis, or we usually say about the x-axis, it's going to give me this blue solid here. Okay, and we call that a solid of revolution because we obtain it by revolving a plane region about some axis. Okay, but naturally, if you're revolving a curve about an axis, the cross sections of that thing perpendicular to the axis you rotate it about will be these discs. Okay, and you can see that if you take a little rectangular slice right here and just kind of see what happens when that one part of the region rotates. It gives me this disc, or because there's kind of a width to it, it actually becomes an approximating cylinder. So this, I can find the volume of these solids of revolution using the same cross-sectional area formula we used in the last video. It's just that the area of the area formula that we're going to use, A of x, is always going to be the area of some circle. Right? Now, you know that the area of a circle is pi r squared. But in this case, what is r? Well, r would be the height of this little rectangle right here. And the reason I know that is by revolving this thing around the x-axis, that height becomes the radius of that circle. Okay? But how do we find the height of this thing? Well, in this particular example, our region was bounded by the x-axis below and a curve above. And so if I find the y coordinate that I would get by plugging x into this function right here, that would give me exactly the height of that little rectangle right there. So the output of our function is what gives me our radius for this circle. That is f of x. That's our radius. So that means that the area formula for this cylinder right here, or this cross-sectional two-dimensional cross-section, I should say, is pi times f of x squared. Again, that f of x is the radius. So if I want to use my cross-sectional area formula from the previous video, then what I'm doing is I'm using that integral. The volume of this solid is going to be the integral of this function. And notice, because pi is a constant, you can pull constants out of integrals. So if I put the pi out here, it doesn't change anything. But pi times the integral from a to b of f of x squared dx. That's just using my cross-sectional area formula for circular cross-sections, okay? So let's try this with an example. Find the volume of the solid obtained by revolving the region bounded by y equals 1 over x, y equals 0, x equals 1, x equals 4 about the x-axis. Now that might seem like a lot to deal with, but it's not too difficult to sketch this. And you generally do want to sketch the region that's being revolved every time you do one of these problems. So I can tell you right away, I'm only going to need the first quadrant of my coordinate plane. Y equals 1 over x is a hyperbola. And here's the branch of it that we care about. It's going to look kind of like that. Accuracy is somewhat important, but not super important here. So I'm not worried about this thing having, you know, the correct scale or any of that. I just need enough information to be able to solve the problem. Y equals 0 is just another name for the x-axis. So I've already included that in my picture. X equals 1 and x equals 4. Those are both horizontal lines. So x equals 1 might be right there. X equals 4. Let's say that it's right here. And now by putting all four of those things together, I can see the region that we're talking about. So that's the region that we're revolving around the x-axis. Another thing it's a good idea to do in these problems is if it has to identify which line you're rotating this region around, because choosing the line in different places will give you different solids and thus different volumes. And we'll look at other lines as well. But for now, if we're revolving around the x-axis, then what I'm going to do is I'm going to give myself this little symbol right here. It's just a little arrow kind of wrapping around the x-axis to remind me which axis I'm revolving around. Okay, that's just going to help keep me on track, basically. All right, so now that I've identified this, can I use this formula? Well, if I'm going to use this formula to find volume, I need to identify what f of x is. And f of x, remember, is the curve that's kind of, in this case, the upper bound for this region. Well, in my example here, this curve is y equals 1 over x. So that's what the f of x is going to be, okay? So setting up my formula now, v equals pi, remember I'm using this formula right here, times the integral from, in this case, 1 to 4. I'm using the x values that are bounding this region. Pi times the definite integral from 1 to 4 of my function, which is 1 over x, but I have to square it. Remember, pi r squared is what we're looking at here, dx. All right, so that's all fine and good. Now let's see if we can work this out. I have pi times the integral from 1 to 4. I can easily square this, and it would give me 1 over x squared, or I could also write that as x to the negative 2 power. Same thing, right? Dx, okay? What is the integral of that? Well, that would be, if I take the antiderivative of this, I would get negative, I'm going to keep the pi kind of in there, pi x to the negative 1 from 1 to 4. Now, you should have had plenty of practice with definite integrals for kind of the more basic functions from Calculus 1. But if you need kind of a quick check to make sure you went from here to here correctly, take the derivative, right? If I did this correctly, then I should be able to go back a step by taking the derivative of what I have here. The derivative of this using the power rule is going to bring that negative 1 down, multiply it to here, that minus becomes a plus, and then I subtract 1 from my exponent. Negative 1 minus 1 is negative 2. So it all kind of lines up, okay? I'm going to rewrite this in a slightly different way. This is the same thing as negative pi over x, and that goes from 1 to 4. If I plug that in, I'm going to get negative pi over 4 minus a negative, so that's going to be like plus pi over 1, okay? And then from here, if I want, I can combine these. This is going to give me 3 pi over 4. That would be kind of the simplest way to write that, okay? All right, that's one example in the bag. Notice that even though there was a few steps involved, none of them were all that difficult, nothing super fancy going on there. It's really just a direct application of this formula right here. So let's do some more. Okay, now in that example, we revolved our region that was described to us about the x-axis. But that's not necessarily the way that it's always going to be. We can revolve around the y-axis, or we can revolve around some arbitrary line that may not be either of the coordinate axes, but maybe something like x equals 3 or something like that. And we're going to look at how to do, those different scenarios. So for this, let's try this. It says, let's find the volume of the solid obtained by revolving the region bounded by x equals the square root of 5 minus y, x equals 0, and y equals 0 about the y-axis, okay? So if I'm going to do this, I'm going to want to sketch this region first to kind of get an idea of what it is we're looking at. Now here, notice x is given as a function of y. It's not y given as a function of x. So you have to make sure you're thinking of that the correct way. And if you're looking at this and you're thinking, I'm not really sure how to graph that, you could solve this for y to kind of put it in a little bit more of a familiar sort of form, I guess. So if I wanted to do that, I would have to start by squaring both sides, which would give me x squared equals 5 minus y. And then I could add this y over and subtract that x squared over, so I could call that y equals 5 minus x squared, or negative x squared plus 5 is another way of thinking of that. However, we do need to be very, very careful here, because if I were to just graph this thing, I can see that it would look like a parabola, which has a vertex at 5 on the y-axis and opens downward because of that minus sign right there. However, I don't want the entire parabola. I only want this half of it right here. And the reason for that is because if you go back up here, if you look at how this function was originally given to you, it is impossible for this x to come out negative, because the square root function only gives you non-negative values. If I were gonna sketch the entire parabola over here, so also giving this left branch, all of the points on that left branch of the parabola have negative x values, which are not allowed by the way this was originally described. So really, I'm gonna add an extra condition here that says x is greater than or equal to 0, which means I'm looking at this guy right here. The x equals 0 and the y equals 0 correspond to the y and x axes respectively. So that means that this is the region I'm looking at, okay? And notice also, we are revolving this thing about the y-axis, not the x-axis. So I'm going to give myself this little symbol to remind myself which axis we're revolving around. So now, because we're revolving around the y-axis, the integration is going to all happen in terms of y. It's not going to happen in terms of x. So that means when I set up my integral, not only does my function, my integrand, have to be given in terms of y, but my limits of integration also have to be y values. So the volume here is going to be pi times the definite integral, and I don't care what the x values are anymore because I'm not revolving around the x-axis. I care what the y values are. And looking at my region, we're going from 0 up to 5. That's the y bounds on this function, 0 to 5. Then I take my function given in terms of y, which is right here, square root of 5 minus y. And remember, for this cross-sectional area formula where we're doing these solids of revolution, it's pi r squared, okay? Remember, as this thing rotates, think of this as my little kind of rectangular approximation, and that thing is going to revolve this way. So this right here is the radius that we're talking about, which is exactly what this function is going to give me. It's going to give me the radius, right? dy, because I'm integrating with respect to y, okay? Squaring this conveniently just eliminates that radical. So now I have 5 minus y dy. And this is pretty easy to work out. So I'm going to get 5y here minus y squared over 2 from 0 to 5. That's what my antiderivative would look like. And then I'm going to think about my limits of integration. Plugging a 0 into these y's is going to produce a 0, which contributes nothing to the answer here. I can just worry about plugging that 5 in. I'm going to get pi times 5, which is 25, minus 5 squared over 2, which is 25 over 2. This is the same thing as 25 pi over 2. And that's my answer, okay? Not too bad. All right, let's see what else we've got here. So the examples that we looked at, the previous two examples, I was dealing with a solid of revolution, but coming back to this page over here, the cross sections of all of those solids of revolution was just a single disc, a solid disc, which is like this pink cross section right here. More generally, the regions that we rotate around an axis might be bounded by two separate curves. So here, if I think of this region right here in blue, as bounded by a particular curve given as a function y equals a function of x. And then another curve down here bounding the bottom of this region, some other function of x. If I were to take that thing and rotate it about this axis, this is probably the x-axis here, then I'm going to get a solid of revolution that has like a void in the middle of it, because all of this empty space right here, if you revolve that around, is just going to create sort of this empty hollow inside, right? And because of that, the cross sections of this solid of revolution here are going to have these holes in them. They're discs with a hole in the center. This shape is called a washer. So that cross section with the hole in it, we call those washers. We need a separate area formula for that washer. Now, if you think of what a washer is, it's a circle with another circle cut out of it. So if we find the area of the larger circle, and then we find the area of the smaller circle, and we subtract the large one minus the small one, that would leave us with the area of that washer. Okay, and that's what we're talking about right here. So if you notice, because I'm talking about two separate curves here, whichever curve is closest to my axis of revolution, that's going to be the thing that gives me the smaller radius, or what I'm going to call the inner radius, which means the radius of this little circle that we're cutting out of our washer. Whichever curve is the furthest from the axis of revolution is going to give me the radius of the outer circle, which I'm going to call the outer radius. And so I can use those two ideas to come up with the area of my washer. It's just the area of the outer circle, which would be pi times the outer radius squared, minus pi times the inner radius squared. This is the area of the inner circle that's being removed, okay? This guy right here is going to be our area formula that we use in our integral for finding these types of volumes. So we have two examples left, which are going to use this idea. I think I'm going to do a part 3 where I work through those final two examples.